Today we're having Atul Sharma, who will be telling us about the hologram of super young males at weak coupling. As usual, we plan to go with Atul to the dinner, and if you want to come with us, you're all invited. We meet at 6:30 here in the lobby of Bloomberg.
Thanks, Warren. Thank you for coming to my talk and braving the snow. Today I'll try to make it interesting. I'm going to tell you about some work that I've been doing over the past year and a half with David Skinner at Cambridge about holography for super young males theory, but in the opposite of the usual regime that we usually work in. I'm going to think about the weak coupling regime. So usually, ADS-CFT operates in the regime of strong drift coupling. So I'm thinking about the ADS-5 CFT4 analog, where the boundary theory is n equals 4 super young males, and it operates in strong drift coupling. This is because in the bulk, this regime of strong drift coupling corresponds to a semi-classical supergravity regime in which you can actually do calculations, as opposed to a stringy regime. Today, I want to talk about holography in the opposite regime of weak drift coupling. So, strictly speaking, I somewhat lied to you. Most of this talk is going to be about strict zero coupling, but during the middle of the talk, I'll make some comments on how you might turn on small but non-zero coupling using some de-instanton effects that were discussed privately. And one thing that a good past example that you can keep in mind to compare with as we go through is the example of tensionless string holography in ADS-3. So this has been quite a successful paradigm in ADS-3, wherein people have found that there's a free theory called the symmetric product overfold of T4. It's a very interesting theory, but it doesn't have a coupling. And people have found that this is dual to a tensionless string theory in ADS-3 cross S3 cross T4. And what I want to present is morally going to be an ADS-5 analog of this, though there's not going to be an ADS-5. That's going to be a bit of a hole. But on the boundary, we're going to have a free theory. There's going to be the free limit of n equals 4. And if anyone has come across these things before, Gaberdial and Gopakumar do have one proposal for the stringy bulk dual of free super young males theory. My proposal is going to look very similar to theirs, but it's not going to be the same. In fact, one of the upshots of my proposal is going to be that it's going to be a much more conventional proposal in nature, in that there's going to be a semi-classical bulk, and you'll be able to use all your intuitions about some classical gravity action, and all that stuff. But this will mean that I'm not going to take a naive zero coupling limit of super young males theory. Instead, I'm going to deal with what is known as the self-dual limit of super young males theory. The self-dual limit is a very special zero coupling limit where you first rescale some of the fields in a clever way before you take the zero coupling limit. And this leaves you with a theory which is chiral, and it retains some of the chiral interaction vertices, as I'll show you later. But nicely enough, there's a very nice string embedding of this theory. Just like standard n equals 4 super young males has a string embedding in terms of D3 branes and type 2B flat space. Witten discovered that this theory can be embedded as the world volume theory of certain branes in a topological string theory that lives on twistor space. So the punchline is going to be that I'm going to tell you that the holographic dual of this theory is a particular twistor string theory with a certain Ramon flux term. And we call this chiral holography because self-dual super young males is a naturally chiral theory. And this proposal sits very snugly in between two other proposals that may be more commonly encountered between twistor holography. So twistor holography is a simplification of the kind of holographic dualities which we usually study, in which we focus attention on just the BPS subsectors. And by physical holography, I mean standard ADS-CFT, where you have everything. And chiral holography sort of sits quite nicely in the middle. In fact, one of Kevin's one of Kevin Costello's bright second-year students, has been thinking about some of these ideas roughly at the same time as us. And he has shown quite explicitly that the twisted holographic duality of Costello and Gaiotto can be obtained as a certain twist of our chiral holographic duality. So the twisted holography that they study is a very nice subsector of chiral holography. On the other hand, chiral holography does contain non-protected quantities. Just like SIM and T4, you can actually study correlation functions of non-BPS quantities. So that's the upshot on top of twisted holography. And as I said, for most of the talk, I'll deal with the lambda equals 0 regime, but I'll give you some hints of how you can turn on d-instantones to turn on marginal deformations of this subdual Sobhanian-Mills theory to take it to full superficies. And I realized that I probably won't be able to finish the whole talk. There are too many slides in the talk, so I decided to just give you one of the application punchlines from the start. So one of the things that we applied this technology to was the study of certain determinant operators, the kind of things that have been studied in these papers. In particular, in this third paper by Simone, Frank Coronado, and Beatrix, they've studied certain determinant correlators at zero Hooft coupling in this particular self-dualing Mills theory. And there they find a beautiful simplification where, again, because there is no coupling constant, they can compute the path integral of this theory in a special gauge called CSW gauge, if you're familiar with that. And this whole path integral of this, so this is a product of half BPS determinant operators, but each of these determinant operators lives in a different BPS sector. So the whole correlation function is not BPS. So this is still an interesting quantity to compute. They reduce this correlation function down to a matrix integral, where you have a matrix which is a k by k matrix, k being the number of determinant insertions. And here xij squared and yij squared just denote the separations of these determinants insertions. So I'm going to tell you sort of a story about the bulk interpretation of this matrix model. And I'll show you how each of these determinant insertions can be interpreted as a very specific brane in the bulk. These branes usually go by the names of giant gravitons in the literature. And I'll tell you how when you turn on back reaction. So here in this picture, I've drawn these red branes, which will host my super Yang-Mills theory. And these blue transverse branes are what we call giant gravitons. And what will happen is that in the presence, each of these blue branes corresponds to one determinant operator. In the presence of back reaction, when you back react by the red branes, some flux will get turned on. And in the presence of this flux, some non-trivial open strings that stretch between these giants get created, which weren't there from before. Basically, the physical interpretation here is that this flux provides some negative tension to the strings, and the strings already have some positive tension because they stretch between branes that are not intersecting, and these two negative and positive tensions balance each other out exactly, so that you can have massless string states even between separated giants. By massless,
Is there some BPS condition for the y's and the x's so that this is calculated?
So each of these y dot phi operators is its half BPS vector, but if you have more than 2 or 3 such determinants, then this correlator is no longer BPS because they're separate BPS sectors. So the only reason this is turning out to be calculable here is because this is at zero Hooft.
Sorry. Yeah, thank you.
That's the magic here.
Yeah.
And usually we say that at zero Hooft coupling, even though we can do calculations, we don't know what the holographic interpretation is. But what I'm going to tell you is that there is a very conventional looking holographic interpretation. And okay, so I realize that on slide 40, I have a cute equation, but I probably won't get slide 40. So let me just give you I wanted to give you a bit of a teaser for why this matrix model sort of harkens for a bulk brane interpretation. Is this big enough for people to see?
It's actually hard to see.
Are there lights?
Lights there?
Probably over there.
No, I think it's
It's perfect.
Yeah.
So, turns out that if you introduce a pair of matrices like this, in which so each of these xi and yi are vectors in R4 or C4, roughly speaking. And David and I noticed that if you introduce certain matrices, which are diagonal matrices, which contain the data of these x's and y, then the equations of motion for saddles of this matrix model can be written in a very suggestive form. So think of rho as the field of that matrix model. The equations of motion look like xij squared. So xi minus xj squared equals yij squared rho inverse ij. And it turns out that if you introduce these diagonal matrices, then you can rewrite this equation as a matrix commutator equation. I'll introduce the spinor notation in a bit. Rho inverse. So the fact, so you can very easily check that because x and y are diagonal matrices, these commutators expand out and exactly give you this equation of motion that would follow from varying that action. But the fact that this equation can be written as a matrix commutator equation in terms of these diagonal matrices already suggests a brane interpretation. Whenever you see a bunch of diagonal matrices which contain the data of some positions, what's the first thing that comes to mind to you as a string theorist? Exactly.
What did you say?
Sorry.
The center of mass on the deep brain.
Exactly. So there are, yeah. So if there is a formulation, then of course there should be some kind of bulk interpretation. So this is the kind of thing that we applied our duality to. And indeed, that's exactly what I'm going to show you later on, if I get it. Okay, any questions? So this is basically a couple of punchlines. So I'll give you a review of self-dual super-Yang-Mills and how it arises as a zero coupling limit. And then I'll tell you its twistor string bulk dual construction. And then I'll tell you a little bit of some subtleties about building a holographic dictionary for local operators on space-time. It turns out that local operators on space-time uplift to branes wrapping twistor lines. So this holographic dictionary will naturally be built in terms of these brane-like objects. And then towards the end of the talk, I'll tell you a bit about giant graviton correlators of half BPS operators. Okay, so let me first begin with a review of self-dual gauge theory. I'll work with spinor notation. So consider a gauge field in 4 dimensions, A, with a tensor subscript A. You can exchange the tensor subscript with a pair of spinor indices. Does anyone want me to explain this more? I can. Okay. So similarly, you can take the field strength and you can replace this with its spinor equivalent, which naturally splits into 2 parts. The anti-self-dual part, which has only left-handed spinor indices, undotted spinor indices, and the self-dual part, which has only right-handed spinor indices. Self-dual Yang-Mills theory is given by a BF-type action, where there's a B field, Lagrange multiplier, whose equation of motion imposes the self-duality equation. The equation of motion of B in this action tells you that the anti-self-dual part of this field strength vanishes, so the gauge field is said to be self-dual. Similarly, the equation of motion of the gauge field itself imposes some Bianchi identity type equation on B. And how you should think about this, and this is the statement in linear theory, which you can keep in your mind, is that when you linearize these field equations, the linearization of this equation gives you an excitation which corresponds to a positive holistic gluon, and the linearization of this equation gives you an excitation which corresponds to a negative holistic gluon in space-time. you should naturally think of A as being the data of a positive velocity gluon and B as being the data of a negative velocity. It turns out that Yang-Mills theory, just your regular Yang-Mills theory that you'll love, can be expanded, can be written as a perturbative expansion around self-dual Yang-Mills theory. And this was discovered by Chalmers and Siegel in the context of computing QCD scattering out. The way this happens is that you add a trace B squared interaction term to this BF theory, and you integrate out B alpha beta. And this gives you Yang-Mills theory up to a complex theta angle, which, depending on your application, you may or may not care about. So for example, this is a very useful starting point for building certain on-shell recursion relations for scattering out, which were used to build this MHV formalism for scattering. The same idea can be made to work for super Yang-Mills theory. So I can expand super Yang-Mills theory perturbatively around its self-dual set. Super Yang-Mills theory has this multiplet, n equals 4 vector multiplet, which contains a positive helicity and a negative helicity gluon as before, but it also contains 4 positive helicity fermions, 4 negative helicity fermions, and 6 scalars. As before, alpha and alpha dot are 2-component Weyl indices, and I and J are indices of SU4, of the fundamental of SU4, so that phi ij is an anti-symmetric tensor in I and J, so it has 6 independent components. Just like for Yang-Mills theory, you can write the action of n equals 4 super Yang-Mills in terms of these B and F fields up to this complex theta term that I'm going to throw away. The theta term only affects the BF bit, but the other bits of the action are the conventional bits. So there's a conventional Dirac term for the fermions and a covariant kinetic term for the phi's, the scalars. And then there are 2 types of cubic couplings, a self-dual coupling and an anti-self-dual coupling, and a quartic coupling. So some of these couplings will drop out in the zero coupling limit problems. And you can also keep a self-dual theta term if you like. Maybe I'll mention towards the end that you can engineer this through an axion type profile in the bulk, just like the usual theta term in n equals 4 is engineered as an axiodel. Probably won't have a chance to do that. So the usual free limit of this theory would be taken, so n is the rank of the gauge group and lambda is the tip coupling. The usual free limit would be taken where you're scaling all fields of the theory by the same lambda and then setting lambda to 0. And that would leave you with a completely free abelian theory. Here's a quote-unquote better limit that we like because we're Twistors. You rescale the fields in a specific way first before you take lambda down to 0. In fact, you rescale them in a way that correlates with their R charge. You don't scale the gauge field A by lambda at all, which is what you would have done to get the free super Yang-Mills. Instead, you rescale all the other fields. The psi tilde goes like lambda to the 1/4, phi scales like lambda to the 1/2, psi has R charge 3 or something, so it goes like lambda to 3/4, and B has R charge 4, so it goes like the first power of lambda. If you do this rescaling and expand out the action of n equals 4, it splits into 2 pieces. One piece that we call the self-dual piece, which is independent of lambda, and another piece which is linear in lambda, which I'm going to call the interaction piece. And the free limit that I'm talking about is the limit as we take lambda goes to 0 to be left with just the self-dual piece. As I said previously, in the self-dual piece, this theory, unlike free super Yang-Mills, is still properly non-abelian. That's the first difference. All the kinetic terms are there, and just one of the Yukawa couplings is there, the self-dual Yukawa coupling. The interaction action and the interaction Lagrangian then contains all the rest of the couplings. So it contains a B squared term that would have Chalmers and Siegel were using, and then it contains the other Yukawa coupling as well as the quartic coupling. Okay, so in the limit that I'm going to take, I'm going to focus on this self-dual action. To find a holographic dual of the self-dual theory, we need a string embedding of this theory. And the key idea that allows us to do this is the fact that the self-dual Super-Yang-Mills theory can be realized as the world volume theory of certain D branes in a topological string living in an appropriate manifold that fibers over twistor space. And then we'll run the usual argument. So this is a very conventional type of holographic duality. We'll take a large number of these branes and we'll back react by these branes. It'll turn out that because this is a topological string, you don't even need to take a near horizon limit because there are no scales to take near horizon in. Instead, you'll just by back reacting, you'll get a theory which has all the conformal symmetry, all the superconformal symmetry that you could ask for. And then we'll study the resulting large N duality that this produces. So now, any questions about this before I go into basics of twistor space? All right, good. Twistor space. So as I said, we'll have to study a string theory in twistor space. So let me remind you what that is. The twistor space of flat space, I'm going to work in Euclidean signature by the way. The twistor space of Euclidean R4 is a suitable open subset of CP3 constructed by removing any particular choice of linearly embedded CP1 in it. The point is that you take CP3, you remove one copy of CP1, and this gives you a manifold which is smoothly diffeomorphic to the spacetime that you like, R4, times CP1. Somewhat like in this picture that I've drawn here, there's going to be spacetime, and to each point in spacetime corresponds to CP1. The CP3 picture is useful because we're going to crucially use the complex structure of this geometry. In the complex structure of CP3, you can introduce holomorphic coordinates in terms of homogeneous coordinates. So this is CP3, so it has 4 homogeneous coordinates. This choice of CP1 naturally splits these into a pair of component spinors, lambda alpha and mu alpha naught. Each of these, so lambda 1, lambda 2, mu 1, mu 2.
If you were to work on S4 rather than R4, would it be simpler that you don't have to do?
You can work on, yeah, that's exactly correct. So on the S4, it's not a Cartesian product, but just this has a name, yeah. It's a vibration or quaternionic vibration or something, but it's a vibration, yeah. Yes, CP3, S4, S2. So I think you would do that if you want to put the boundary CFT on a proper S4, which is probably the correct way to think about it. But this is just easier. Okay, anyway, so so here, the remove CP1 basically is telling me, the CP1 that I remove in this choice is the CP1 where both lambda alphas are simultaneously 0. And this is useful because if I remove the place where both lambda alpha are simultaneously 0, then I can use lambda alpha as homogeneous coordinates on this CP1 factor. So that's basically what happens. They become homogeneous coordinates on these CP. As I said, there's a diffeo from PT to R4 times CP1. So this diffeus can be encoded in terms of twistor lines. To each point in spacetime, x alpha alpha dot, you get a whole copy of CP1, which is a linearly embedded CP1 given in terms of these homogeneous coordinates by these incidence relations constructed by Penrose in age-old times. And the running philosophy in the whole subject for the last 20 years or so has been that integrable theories on Euclidean R4 can be obtained oftentimes from certain holomorphic theories placed on twistor space and then compactified along the CP1 factor. So this reproduces certain integrable theories, the kind of self-dual theories that we are interested in. The same story can be repeated for n equals 4 superspace. So you can introduce an n equals 4 super twistor space. You replace CP3 by projective superspace. CP3/4, then you remove a particular locus, again corresponding to lambda alpha equals 0, which in this case is a CP1/4. And this gives you something that is diffeomorphic to chiral n equals 4 superspace times CP. Homogeneous coordinates, again split into, so firstly, homogeneous coordinates split into a Grassmann even and Grassmann odd bit, which is the twistor bit, and so there are 4 twistor coordinates, and 4 Grassmann odd coordinates theta I, so I runs from 1 up to 4, is the fundamental of SU4, as I said before. And the notion of twistor lines get replaced by super twistor lines. There's a different thing called twistor superline, which I'll come back to, which is not a super twistor. So a super twistor line is still coordinatized by a single bosonic pair of coordinates lambda alpha. And again, mu is x lambda. So there's a chiral superspace version of x that appears here. And eta is given by some chiral superspace, some space-time Grassmann coordinates theta alpha I times lambda alpha. And because we're working in Euclidean signature, the theta and theta tildes are not complex conjugates of each other, so it's quite convenient to just restrict to theta tilde equals 0. So you can just think of the super twistor lines as being mu equals x lambda and eta equals theta lambda. The key idea now is that the space-time action of self-dual superioring modes that was looking very complicated uplifts to a very simple holomorphic Chern-Simons theory on super twistor space. So there's a nice measure and there's a holomorphic Chern-Simons type functional. And here I'm gonna, for the rest of the talk, I'm just gonna set the self-dual theta angle to 0. So this is just the self-dual Yang-Mills, super Yang-Mills bit. Roughly, just to give you an idea of how this works, this field, curly A, expands as a superfield in these etas. Each coefficient field here is an anti-holomorphic one form on twistor space in the complex structure of CP3. Compactification along the twistor lines reproduces for you n equals 4 self-dual super Yang-Mills. And each of these coefficient fields, the 0 modes of these fields along the KK reduction on CP1, give you one by one the fields of the n equals 4 vector multiplier that you're familiar with. And, okay, so the key idea now is to take that action. Once you've seen the holomorphic Chern-Simons action, and if you know your string theory, you know that it looks very much like a string field theory. You want to realize this as some kind of string theory. And Witten realized this as a B model placed on an appropriate. So originally this is something called twistor string theory. Originally this was realized as a topological B model placed on a super Calabi-Yau manifold, CP3/4. But I'm going to use a more modern formulation, which has been sort of known in the community, but has been written down nicely recently by Wittelston, Costello, and Zheng in their paper, where twistor string theory is thought of as being a topological B model that lives on a Calabi-Yau sevenfold. So you take PT, which is a subset of CP3, and you take a particular rank 4 vector bundle such that the total space of that is Calabi-Yau.
So I assume now we're not going to have the super Yang-Mills theory, will we?
We are going to have the super coordinates eta show up again, and they'll be because there are 4 normal directions of -1. So there's going to be one fermionic coordinate associated to each.
Will we really get the super informal algebra?
Yeah. The PSL4/4? Yeah. We'll get exactly the same holomorphic Chern-Simons action from this picture. There's going to be 4 normal directions, so there are 4 Higgs fields, and then multiply them.
So the space is still closely related to CP3/4.
Well,
Sorry?
the fermions have been turned into bosons.
The bosons. Yeah, then the space.
Yeah. Kevin uses the word fermionic T-duality. I do not know what that means, but that means anything. Yeah, fermions we turn into those. So here's a picture, whether it's nice or not, you can decide. So the picture is going to be that there's going to be some twistor space, and there's going to be a rank 4 bundle with C4 fibers. And I'm going to wrap n d5 branes. Just a note of convention, my brain numbering is sort of a historical artifact of working with RNS strings. So d5 brane is 6-dimensional. So it wraps the 6 real dimensional twistor space. And I'm going to take the number of these branes to infinity. And so for any given n, it engineers the twistor holomorphic Chern-Simons action for un ST super Mills. But I'm going to back react by these branes in the large n limit and then see what comes out in the bulk.
I think I have a very basic question. Why is your world volume increased in dimension? Where is the step? Since we went from 4D super Young Mills to now 6D world volume theories. So
yes.
where did you get 2 dimensions?
Oh, so R4 times CP1. CP1 is S2, so that's 2 extra dimensions.
Okay.
So that's twistor space.
I think the idea is that since the O minus 1 is negatively twisted, your modes are going to be trapped at the 0 section. So the physics will still live on CP3.
Yes, but there's still going to be 4 fake Higgs fields, right? Even though it can't actually move. Yeah. I'm going to get some water as a cat.
Sorry, that's question. It's important that it's a holomorphic theory in this space, right? That reduces some.
I think the brane is going to be wrapped, or even the brane's wrapped on the 0 sections. So the branes just live on CP3, which means that the boundaries of string logic are on CP3, and the rest don't get too much far away. But the O minus 1 to the 4 is needed to cancel normalize.
What's the my?
Where? I'll come to the minus ones. This is not the end. I'm going to tell you more. Don't worry about it. I'm not that cool. Okay, so now let me tell you more about the twistor string bulk deal. So the bulk geometry, as I said, consists of twistor space and the 4 minus 1 fibers over it. To make this a bit more explicit, let's place some coordinates. So use ZA equals lambda mu as before as coordinates on twistor space, and WI as coordinates on the 4 fiber directions. And the fiber index is going to get identified with the SU4R. Because of this O minus 1, what this O minus 1 means in homogeneous coordinate language is that Z and W are identified with these particular rescalings. Z comma W is equivalent to TZ times comma T inverse tau. What this allows you to do is to construct a Calabi-Yau-7 form, which is the projective volume form along twistor space times the fiber-wise volume form on the C4 fibers. And this projective volume form has homogeneity degree 4 in Zs, and the D4W has homogeneity -4 because of this inverse here. So this is a globally well-defined weightless volume form, which ensures that this geometry has a trivial canonical. I'm going to tell you a little bit about closed twistor string theory, but it's basically the closed topological string in this background if you don't need to, if you don't want to interact with the details. But it's very easy to write down as opposed to RNS string, closed string field theory, which is extremely hard to write down. The field content of this theory consists of all possible anti-holomorphic differential forms valued in holomorphic vector fields. X here, sorry, I didn't say, but X is going to be my notation for this total space, of this vector. So X is my form. There's a very simple action for these fields. So you combine all these fields as a polyform, and then you can write this action, you can write the action with these in a form that resembles the Chern-Simons action functional. This is also known as Kodada-Spencer gravity in 3 complex dimensions, but Costello and Lee sort of generalized it to higher dimensions, and they named it after the original authors, which is basically the equations of motion. The equations of motion of this theory are certain, well, they're called Motor-Cartan equations. So they basically tell you that certain complex structure deformations and certain generalizations of complex structure deformations of this target space are integrable. So if P and Q are 1 here, that field corresponds to a Beltrami differential, and then the other fields are just some kind of appropriate generalizations in Calabi-Yau. And this action has a weird del inverse in it. Del here is the divergence operator with respect to the volume form that I showed. The way to understand this is there's a common phenomena in string Ramon string field theory, where you can write the action in terms of the Ramon field strength, but then it turns out to be non-local. So the way to interpret this is that the Ramon field strength is derived from a gauge potential. So in terms of this C field gauge potential, the action would be local. You don't need to remember any of this. I will never invoke this in the rest of the talk. This is just to give you an idea that this closed string theory is completely explicitly, at least this tree level closed string field theory is completely explicitly known, and then you can, of course, derive the loop level things carefully.
Berkovitz and I thought that it described conformal supergravity.
Yeah, so this is something that David understood better than me, but I think what's happened, and the reference was something by Seidlin, but what was happening was that in ADS5 cross S5, supergravity in ADS5 looks like conformal gravity on the boundary of ADS5. So that's what's happening. The same thing is happening here. This bigger theory, when restricted to PT, is looking like conformal supergravity. But actually, the closed string fields can propagate in the 7 complex dimensional bulk of this theory. And I'm not going to talk about this, but you can explicitly work out the Beltrami degrees of freedom that you worked out in your paper with Nathan. And you can show that they're exactly dual to things like the stress tensor or the R symmetry current. So this is like the holomorphic analog of the graviton mode.
Paul, I just to make sure I'm understanding of Paul. If I compute a multi-trace amplitude, am I going to see a conformal graviton pole?
So you will, but it's what we're trying to say is that it's not a pole from conformal gravity in 4-dimensional space-time. The gravitational theory was never conformal gravity. It was secretly this higher dimensional gravity all along.
But you do see, you're not contradicting the statement that you do see a conformal graviton pole.
Yes, you will see a pole, but it'll be a pole of this weirder gravitational theory.
What if you reduce on the CP1 again?
I tried to do that, but I failed, so I cannot tell you what happens. I was going to comment at the end of the talk that hopefully it's related to some kind of tensionless phase of string theory on ADS5 process 5, because the boundary theory is the zero coupling limit of CPI.
So it's not that after reducing you get conformal gravity?
No, because it's not going to live on R4. It's going to.
It's R4 cross the tail.
Exactly. It's going to be R4 times some S5 maybe, or ADS5 cross S5. So the O minus 1 of the 4 directions here are exactly the analog of the S5 in ADS5 cross S5. But yeah, we can talk more about this. I can help clarify. Yeah.
So your commutator is a Lie bracket,
Yeah, this bracket is something called the Schouten Nijenhuis bracket, which is just a generalization of the Lie bracket to polyvectors. Polyvectors are like the exterior algebra on vector fields.
But this equation of motion is still a holomorphicity equation. So there's some limit of this thing which reduces to the nonlinear graviton equation or not.
So this is in 7 complex dimensions. If you do this in 3 complex dimensions,
Then this will be the counter.
yeah, it's not a limit, more like a subsector. Like this has double the amount of solutions. Okay, this is also related to the conformal gravity thing.
It contains self-dual gravity.
If you take this equation and restrict all the fields to live on PT, so these fields psi will be functions of Z and W based on pi. Restrict everything to W equals 0. Then this equation gives you some equation on PT. That's what these people thought was conformal supergravity. And of course, Einstein gravity sets as a sub-solution. So the sector of some solutions. That's like the sector of Hamiltonian complex structure. Okay, so now I can finally come to the new stuff. So we're gonna, okay, this picture was also sort of new, but it has been told to us by Kevin for a few years now. This that you should replace CP3/4 by O-1 or P3. But let me come to the new stuff where we back react by these branes and study what happens. So zero section Wi equals 0 is a copy of PT as I was drawing in my diagrams. You wrap ND5 branes along that 0 section. That adds a source term on the right-hand side of these supergravity equations. This source term is supported at W equals 0. You can solve this field equation in terms of the fundamental solution of the d-bar operator. And basically, you get a solution which has a pole at W equals 0, which tells you that there's a delta function source at W. This is the back reaction. And note that this is a 7-form back reaction. Just like in ADS5 process 5, you get a back reaction which is a 5-form, so middle dimensional. In this case, our real geometry is 14 real dimensional, so we're getting a 7-form back reaction.
Could you explain what the symbol that?
I'm sorry, I should have said that. So basically, the back reaction is a anti-holomorphic differential form times a polyvector field, where it's convenient to replace polyvectors by differential forms by taking the interior product with the holomorphic volume form. So basically, omega is D3Z D4W. The Hooft symbol just takes all the vectors and contracts them into the differential form bits. And if I write this in terms of vector fields, I need to work on an affine patch of PT and give you separate expressions. It's just nicer to do it. This Hooft is just contraction along the vector and covector indices.
So is this particular solution a solution of the self-dual sector or a solution of the bigger sector?
This is a solution completely of along the fibers. So this has nothing to do with
Oh, you cannot project, okay, because you have D4
completely along the fibers.
You cannot project it down to the self-dual.
Yeah, if you do that, you get 0. That is a problem, but I won't mention it. Okay, so coming back, the duality conjecture, I've stated a bit more cleanly, is that UN n equals 4 self-dual Yang-Mills is dual. The B model on this space, so strictly speaking, remove the brane locus because the form that its source was singular along that. So the B model in this space minus the brane locus with n units of the 7-form flux that I showed you previously. It's easy to match the symmetries already. The SL4 conformal symmetry acts on twistor space. Here it's slightly nicer to work with the CP3 picture because the symmetry acts more nicely on S4, but basically the SL4 conformal symmetry acts on twistor space. So that's where that comes out from. And the R symmetry is just a symmetry that rotates the fibers among them. So the bosonic symmetry groups are easily matched. The fermionic symmetry groups can also be matched, but I refer you to the paper for that. You can derive conserved currents for all of these PSL4/4 conformal symmetries, and you can also show that they're holographically dual to modes of the Beltrami operators in the multiplet of the Beltrami differential.
So is there any obvious relation in this space to PS5?
So we tried for a long time to try to see if there's any relation, but we couldn't. PT has a relation, PT is related to R4, which is like the boundary of ADS5. The O-1 to the 4s, if you projectivize them, They have another CP3 in them, and you can think of this as the twistor space of an S4 that lives on the equator of the S5, roughly speaking. But somehow there's a bulk direction, which is the overall scale of the O-1 of the force. And somehow that has something to do with ADS5, but we haven't been able to pin that down. It would be very interesting to see whether this larger theory on this 14-dimensional space is some kind of 4 extra dimensional uplift of tensionless strings in ADS5 process 5 in some weird limit, maybe with some weird theta, some axial dilaton terminal. But that's like a completely open question. We're still thinking about it. But we tried a few like algebraic geometry tricks, but nothing seems to work.
So the non-trivial content of the conjecture things like insertion of giant gravitons, because
Yeah, so I'll come to that next.
the basic statement of subtotal young mills living as a theory on PT, that's the first part of the talk.
Yeah. So this is the basic duality conjecture, and now I'll tell you the holographic dictionary. So, since I only have 15 minutes, let me go faster. States of the bulk theory in holography are usually thought of as being related to states of the boundary theory. In this case, the boundary theory effectively is n equals 4 self-dual super-Young mills once you reduce along CP1. So states of the boundary theory are in one-to-one correspondence by the state operator correspondence of the CFT to local operators on space-time. But local operators on space-time, unfortunately, uplift non-local operators on twistor space. For example, as I told you previously, there's a not-one form field phi ij whose zero mode along the along the CP1 is the space-time scalar big phi ij. If you use this integral formula and take your favorite trace phi square type operator, then it uplifts to a bilocal operator on the sphere. And this is very annoying because the duality operates at the level of the twistor space theory, and I would have liked to relate single particle states of the bulk theory to local operators on twistor space, but that won't do. Instead, what's going to happen, and this also works in the RNS string, so it seems to be a bit of a evidence for the fact that this is the more fundamental thing to do. We're going to encode the single trace operators in determinant operators. Somehow, I'd like to believe that this is telling us that it's the determinant operators which are more fundamental than the single trace operators. And these determinant operators will be dual to branes in the bulk. And this is one of the things that Beatrix and Simone and Frank use in their paper. Maybe I won't tell you about that. Let me not tell you about polyvectors. It's a larger superspace, which is very complicated. Maybe I should. Okay. Just stop me when you're bored. Okay. So the correct way to think about branes in this space is in terms of a slightly extended target space, which also comes back to the CP3/4 pictures. I want to emphasize this a little bit. So remember that the closed string field that I told you about were polyvectors on my bulk X. You can think of polyvectors of X as functions on the parity reverse cotangent bundle of X in the following way. You introduce a pair of Grassmann variables, epsilon a and eta I, which carry co-vector indices. So in that sense, they're coordinates on T star X, but they're Grassmann owned. And you put them in one-to-one correspondence with the generators of the vector fields in space. If you do that, then you can replace each vector field on X by this Grassmann, this function of these Grassmann-owned coordinates, epsilon and eta. And these etas are the coordinates on P3/4 secretly. And these coordinates are related by a relation that tells you that the Euler homogeneity vector field is trivial. So it's a 7-dimensional fiber of this cotangent bundle. This cotangent bundle, this picture is also the right picture to think of D branes. It comes equipped with an appropriate symplectic form by virtue of being a cotangent bundle. And branes precisely wrap Lagrangian submanifolds of this shifted symplectic manifold. For example, the original D5 brane that wrapped super twistor space wrapped the Lagrangian submanifold where I set W to 0 and epsilon to 0. And then the leftover coordinates on that super space were exactly Z and eta. So it gave me a holomorphic Chern-Simons theory on the space of Z and eta, which was CP3/4. Okay, so that's how you recover CP3/4. So then Edward discussed d-instantons in order to go beyond the self-dual sector. And in the original twistor string picture, these d-instantons are D1, but thought of as D1 branes that wrapped twistor lines inside twistor space. But actually, in this larger picture, they happen to be D9 branes that wrap a line in twistor space and the fibers of O-1 to 4 above that line. And you can find a profile for this, the embedding of this D9, which lives in this quadratic variety and is also Lagrangian, just like the original D5 branes. And you can show that this intersects the original twistor space branes in exactly a super twistor line. When you set W to 0 here and epsilons to 0, you're just left with the first two equations.
Are we getting back at some point to what you said about trace operators being non-local and how you would solve it?
Yeah, so in the next slide. Strings on the D5, D9 intersection engineer exactly the current algebra that Nair used and then Edward used to compute MHV Park-Taylor, the Park-Taylor formula for MHV amplitudes. And they do this by the following procedure. There's some action for some 2D strings that are localized on the intersection of the brane bell volumes. When you integrate out these strings, that leaves you with a determinant insertion in the path integral of n equals 4 ST Engels. When you expand this out, it produces a single trace term which coincides with the interaction Lagrangian. So that's how you go beyond the self-dual sector, plus some junk multi-trace terms. I wanted to sort of mention a student of David Skinner's who also found a way to kill these multi-trace terms very recently I've sort of reinterpreted what he did as a D9 anti-D9 pair insertion. So if you're interested, I can tell you more about his work. He's a postdoc in Edinburgh now, but he is going to be on the market next year, or next cycle. Now let's come to half BPS operators. As I said, I'm not going to good, I told you already about that. So now you can keep wondering about that. So let's come to half BPS operators. Half BPS operators are constructed as follows. You take SU4 and you split it into two parts, SU2 times SU2. You do that by taking the 4-component index I of SU4 and splitting it into a pair of 2-component indices A and A. Half BPS primaries are single traces of this form. Phi are 6 scalars and Y is a null 6 vector that I've contracted into phi. It takes a particular form such that this Yij is parameterized in terms of some arbitrary 4 vector in some auxiliary R4, so Yaa dot. This Yaa dot is what you need to keep in mind. It's very hard to uplift these local operators on spacetime into local operators on twistor space. We haven't found any way to do so. But if you arrange them in determinant generating functionals, then you can again uplift these. Then you can uplift them as another set of chiral algebra, which was discovered by Coronel and Newman, and also previously building on ideas from Chota and France. Any questions about this generating functional?
That's the definition of it. This is for any determinant, right?
This is for so this only contains a single scalar, y dot phi. So this determines.
Writing out trace logarithm Taylor series.
Yes. Yes. So this is like when you take this determinant, expand the log, it gives you a generating function for these single traces. For any trace, yeah. That's.
And the reason it can be uplifted is because the determinant comes from the fermions that you can integrate out.
Indeed. I'll tell you that. And then, then I can stop depending. Okay, so now we're going to encode these as branes in the bulk. specifically as something called giant graviton branes, so half BPS giant graviton. Let me tell you what these branes are, and then I'll relate them to the determinant of pairs. I'm going to consider branes that arise as D5 branes. So there'll be 6-dimensional branes that wrap, again, the twistor, a particular choice of twistor line corresponding to a point of space-time, and 2 out of the 4 O-1 directions. So they sort of split the O-4 into 2 pieces. That's why they're half BPS. So you split Z into lambda and mu, and you can similarly split W into a pair of coordinates tau and nu. And similarly, you can split the fermionic coordinates into epsilon and eta. So roughly speaking, along the twistor directions, mu is orthogonal to this brane, lambda is along the brane, tau is going to be along the brane, and nu is going to be orthogonal to the brane in the 5 directions. I'm going to call it a D5 prime to distinguish it from the original branes. And just like for the D9, D instantons, you can find an embedding of these giant gravitons, which live in the quadratic variety that I was talking about and are Lagrangian in the superspace, in the supertotal space. They are the line. They depend on x, y, and some coordinate theta, which is a coordinate of chiral superspace of this half BPS sector on spacetime. I'm going to set this theta to 0 and focus only on chiral primaries, which their matrix of paper also tells you how to encode these thetas. So you can also do that in principle. So these branes intersect the original twistor space in twistor superlines. And I call these superlines because now they're parametrized by a pair of bosonic coordinates lambda and a pair of fermionic coordinates eta. Okay, so that was the difference from the original lines. And basically now you work out the string theory on the intersection. Since the intersection in the super sense is a CP1/2, what you get is now what these guys call the CP1/2 model. I should find a better name. So the strings on the D5, D9 intersection are functions of the CP1/2 coordinates. So they're naturally superfields in the 2 etas that coordinatize CP1/2. And without belaboring the point, if you just integrate out these things, this would give you a determinant of y dot phi on R4. But you can get the 1 in the generating functional by turning on a particular open string web on these giant gravitons. And this basically sort of shifts the 0 mode a little bit so that you get a determinant of 1 plus y dot phi on R4. There's a choice here, lambda star, which is a reference spinner, which is analogous to the CSW gauge reference spinner. It's like an HL gauge, which drops out of physical quantities, like it dropped out of the determinant when you integrate out these values. Okay, so here's a summary of the holographic dictionary. The interaction Lagrangian that takes you away from the subdual sector is inserted by inserting D9 branes, or more sorry.
So the takeaway is that because determinants come from local actions,
Yes.
whereas these traces previously we had problems with.
Yes, exactly. What's happening here is that when you take this determinant and expand it out in the twistor space fields, they contain integrals automatically. So they're integrated over this CP1. When you expand the determinant, it reproduces these polylocal integrals over the CP1. And then term by term, it turns into a local orbital spacetime. So half BPS operators are encoded in D5 giants that linearly wrap 2 out of the 4 O-1 fibers. And we haven't figured out what less BPS operators correspond to, but recently I was reading this paper by Mikhailov from 2000, and he knows how to write less BPS giant gravitons. So I'm just going to work that out in the coming months, I think. So hopefully, hopefully ideally non-BPS operators as well. Okay, if I'm allowed to take 5 to 10 more minutes, I can tell you about correlation functions of these determinant operators. These determinant, okay, so to remind you, what Karenhoek, Correlators, and Muehlmann showed, that at 0 Hooft coupling in the self-dual theory, you can reduce the calculation of the correlator of k such determinants in different RVPS sectors down to a matrix model. And what we set ourselves, the task that we set ourselves to do was to find a bulk interpretation of the saddles of this matrix model. The hope is that the saddles of this matrix model map to shapes of giant gravitons. And that sentence gets a bit refined. So they'll map to certain open string configurations of giant gravitons. Okay, the bulk dual of this is going to be the world volume theory of these giants. And we're going to set up this world volume theory in a couple of steps. We will start with a bunch of coincident giants. So again, this slide is going to be the physical lesson that you can take away, and then you can forget about all the calculations. The physical lesson is that to set up the world volume theory, you start with placing all the giants coincident. And this engineer, so there are k-set giants. So this engineers complexified UK gauge theory. So a particular GLKC holomorphic Chern-Simons theory on the world volume theory of these giants. First, we separate these giants by Higgsing. And this Higgsing is exactly what brings in those position center of mass matrices into the game. And as you can see, there are some strings here that are localized to the brane intersections. The third step is to study back reaction. And when you back react, these strings tie up and remain massless, even though they're stretching between separated giants. So I'm saying massless, but I guess the correct word is that there's a non-trivial solution of the equations of motion. There is a mass term, but there's a negative mass term, and they balance each other. Okay, so the D5 branes wrap the total space of a pair of O-1 directions over a twistor superline. We start with the twistor superline of the origin, and then we move them along the X and Y directions. The theory is, again, a holomorphic Chern-Simons theory. Is always a holomorphic Chern-Simons theory, free-level open string theory. The index, the gauge index on this is now the label of the determinant operator, I and J. So I and J now run from 1 up to little k. The action of this theory is holomorphic Chern-Simons. As I said before, there are 3 bosonic directions and 4 normal fermionic directions, 2 epsilons and 2 etas. So firstly, I need to tell you what are the Higgs fields so that I can separate these giants. That's easy. I've told you that each of these fermions, so there's 1 fermion per normal direction to the giants. Each of these fermions are in 1-to-1 correspondence with vector fields. That's how you should think about them. So the term that is linear in the fermions, you should think of this as being m alpha dot d by d mu alpha dot. So a particular normal vector to the brane, and n a dot d by d mu a dot, two of the normal directions in the O-1 directions. So these are the Higgs fields. And you give them these particular set of diagonal webs, which take them from the twistor superline of the origin and move them stack, stack, stack to their final locations. And finally, we come to the most interesting physical effect, the effect of back reaction. Here, I encountered a little bit of trouble in using the original back reaction that I've shown you. So what I did was a bit of a trick. And we can discuss whether you believe this trick or not. But here's a very easy way to compute this back reaction. Basically, what's happening is that this is the original Chern-Simons action, and the back reaction generates a determinant term that gets added to the action. The way this happens is, in analogy with the closed string back reaction, you can work out the back reaction of the open strings that live on the brane intersection. Integrate. If you know the words open-closed duality, then the idea here is that holography should be thought of as integrating out the open strings that live on the branes, and integrating out procedure is somehow supposed to replace them with a closed string flux. So if you integrate out the 5 strings that live on the original D5 ring trapping twistor space, they generate the closed string 7-form flux. To compute this back reaction effect, what we did was we simply integrated out. There's an action that these strings contribute, these 5 prime and 5 prime 5 strings. If you integrate them out, then that deforms the open string field theory on these branes. And that deformation is, again, exactly a determinant type of brane. So just like originally we were getting determinant insertions in the theory of these d5 branes wrapping twistor space by integrating out the fermions, you can do the same thing on the other side. You integrate out the fermions by coupling them to the theory that lives on this brane, and that generates this log difference. And that's where the dependence on n enters, for example. So that's very important. This theory doesn't know about that. At this stage, we can turn on the Higgs webs, and that finishes the setup of the giant graviton well volume theory. Now, let's come back to the matrix model. As I told you earlier, the matrix model equation of motion can be beautifully recast in terms as a commutator equation in terms of exactly these matrices that encode the positions of these giants. And these are motivated by a lower dimensional example that Kashabujic and Davide Gaiotto worked out for determinant correlators for operators in the same half BPS sector. The same quarter BP, 1/8 BPS, sorry. Anyway, so there it's a slightly simpler commutator equation for them, but we get like a double commutator equation. And I won't give you a proof of this, but you can very easily sort of solve the equations of motion of that Chern-Simons theory by putting in ansatz. And you find that every solution of the matrix model saddle equations maps to a configuration of open strings on the giants. So rho is the data of some non-trivial saddle of this matrix model, and that gives you the sort of profile of open things, the kind of things that I was drawing earlier for you. These are giants. Then there'll be open strings that stretch between the ith giant and the jth giant. And this will be encoded in rho ij. Okay. So let me finish by telling you a few key lessons. Unlike the supergravity regime, in this tensionless regime, so I'm putting tensionless in quotes, but I mean like the zero diff coupling regime, we're able to find giant graviton configurations at arbitrary multiplicity k of the determinant of x, or arbitrarily many determinants. In the supergravity regime, people have found giant graviton solutions corresponding to the correlate of 2 determinants and maybe 3 determinants, but it's very hard in that case because you have to do it case by case, look at the solutions for the shapes of the giant gravitons. Here, this zero coupling analysis is teaching us a lesson that perhaps you should work with the DBI action, you should Higgs the whole thing, and then you should just look for a solution of open strings in a non-abelian sense, as opposed to looking for shapes of a single sort of amoeba-like brane that can reach out various places on the boundary. Saddles of this matrix model show up as deformations of the trivial open string vacuum, sort of places the giant in a different vacuum which has some strings between the giants. And we were able to recover most of the matrix model from the on-shell action of the giants. I can recover the log-det rho piece, so the matrix model has 2 pieces. I can recover this piece. I was having some trouble recovering the Gaussian piece, but if anyone is curious, I can tell you about it and maybe you can make some suggestions. I recovered the Gaussian, but a slight extra discrepancy. So maybe there's an easy way to resolve that. And of course, the lesson question what this brings up is whether we could use these. So the B model is a great toy model for these calculations, and the ultimate lesson is whether we can import any of these toy calculations into RNS strings at strong coupling. Okay, so as an outlook, let me just close on some of the other applications that you might imagine this duality having. I told you that you can use D9 branes to insert, to go beyond the self-dual sector. But a slightly better way to go beyond the self-dual sector is using the amplitude Wilson loop duality, which was found a strong coupling by Alde and Maldacena, but there's a weak coupling version of this as well that was constructed by Mason and Skinner. I think there might be, or maybe Sakat fans. I don't know exactly who did this first. But you can embed this weak coupling amplitude Wilson loop duality, or at least the Wilson loop side of this duality, into this holographic setup. The holomorphic Wilson loop turns out to be a loop of D9 branes now. Because on the twistor space, the holomorphic Wilson loop looks like a polygon, but each polygon is the intersection of a huge D9 brane with twistor space. And in fact, you can even write down a sort of matrix model for this Wilson loop, which we just teased in the conclusion section of our paper. Hopefully, I'll come back to that at some point. But just like the half BPS correlators had a nice matrix model, it's unfortunate Nima is not here. Okay, just as the half BPS correlators had a nice matrix model expression, you can find, in this case, a two matrix model where the matrices rho and sigma, and the coefficients of this matrix model's kinetic terms are what are called R invariants. So there are 5 particle objects that encode the n equals 4 scattering amplitudes. This is a tree level n equals 4 scattering amplitude matrix model. So hopefully we'll explore this a bit more and see what is the bulk dual. So we are expecting that saddles of this matrix model will now correspond to configurations of open strings on these D9 branes, and hopefully their mole volume action reproduces the amplitudes. And finally, let me end by saying that the original ADS-CFT duality is good because it can produce great, miraculous, strong coupling results. This duality, on the other hand, is good because you can do calculations on both sides of the duality and test it even in non-BPS sectors. So, for example, one of the things that I'm doing with some postdocs at Harvard is looking for the hologram of so there's people are probably familiar with the deconfinement transition for n equals 4 CP angles at zero coupling or at weak Hooft coupling in finite volumes. And this is computed shown using thermal partition function at weak coupling, which is not a BPS quantity. So you can't really match it with anything to my knowledge, you can't match it with anything in regular ADS-CFT. But now in this duality, we hope that there's some kind of mysterious Hawking phase transition that we can nail down. So that's one thing that we're trying to do. This also provides a laboratory to study bulk duals of finite n effects, because there are many finite n effects like giant graviton expansions, Fortuna states, etc., that people study in the boundary theory at weak Hooft coupling. So people compute cohomology of operators in the boundary theory at weak Hooft coupling. And perhaps we might be able to do this in non-BPS sectors or 1/16 BPS sectors to see what their duals are in this slightly simpler holographic duality. And finally, okay, there's a Cement T4 version for ADS3. This is supposed to be the analog for ADS5, but it's natural to wonder if these kind of constructions could also work for other holography examples like APJM. And Anna was saying, or who was saying, ultimately, we would also like to relate this whole duality to tensionless strings in ADS5 process 5, but that's like a completely open thing. We haven't made any progress on this, but I'm looking to conversations, of course, looking forward to conversation, and thank you for listening. Any other questions?
Yeah. Sorry, I'm so sorry. I didn't quite get the point of the saddle. So there was a matrix model that Simon Flanagan matrix found. This is a saddle point. What's the purpose of the saddle? I mean, you're interpreting this as the D9, sorry, the D5 world volume theory, but what's the actual application?
The application is to the calculation of this half BPS correlation function, and then trying to give a holographic dual to that at zero coupling. So you compute this determinant correlation function.
Right.
And in the boundary theory, you can reduce the calculation down to a matrix model. And what we were trying to see is whether this has a holographic dual, just as a test of our duality.
Right, but I saw these are the D1 instances.
They're similar to the D1 instances. Yeah, they're like these partially. There are 4 instead of 8 dimensions. Two instead of 4 dimensions.
But can we compute something like an n square MHP amplitude? In the original story, the intentons give you corrections to the self-dual action. And so presumably you can do NMHV by inserting one of them. How about the full NX?
That will reproduce for you the MHV forms.
So you can insert both. So these are like insertion of two of these giant gravitons, or these different?
No, for that you will use the.
Sorry, I think in that story
That you will use these D9 branes, which engineer the interaction Lagrangian. You can also use the giant gravitons. So this was something that I only learned from these guys' papers. But if you take the half BPS operators, trace phi squared, and you act with supercharges, and you go down them supermultiplet, you get the interaction Lagrangian from that as well. So you could also in principle use this, though I would have to do everything with super Grassmann variables. It should be possible.
I have a quick, sorry, I'm very confused about how this duality works with self-dual Yang-Mills, because you're saying before that you do have the ghost sectors in multi-trace operators. So if you're having ghosts contributing for multi-trace operators, in what sense is this actually dual to self-dual Yang-Mills? Because self-dual Yang-Mills, sorry, not ghosts, conformal graviton. All right, I'm just saying, before I asked whether you had a conformal graviton appearing if you did multi-trace, and you said yes. So how can this be dual to self-dual Yang-Mills beyond the single trace sector?
So what's happening here is that I'm trying to construct the bulk dual to just the single trace interaction Lagrangian. And so we're trying to see whether single D9 brane does the job. It comes close, but it's secretly dual to a more complicated combination of multi-traces. If you want just the single trace operator L-int, then what you have to try to engineer is not det, but log det. And one way to engineer the log det is to use a carefully constructed D9 anti-D9 pair, which sort of kills most of the determinant, but leaves you with a log. You have to do some insertions and some tricks to do that, but it does that. So the interaction Lagrangian, you should think of it as a marginal deformation of the free theory. You would add it to the action of your free theory to generate the full theory, but you can then start bringing that down in the path integral perturbatively. And each insertion of L-int, you should think of it as being dual to a D9 brane, or this more carefully constructed D9 anti-D9 pair. And then amplitudes computed using correlators of these L-int insertions will correspond to certain open string solutions on those D9 branes and their non-shell action on those. There'll be a holographic duality. So it's somewhat different from the original informal gravity interpretation.
Okay, well, I remind you we're going to meet for dinner at 6:30. Let's thank Atul again.